Hello and welcome to Calculus Tutorial again. We are entering into a time here where we're going to learn some new derivative and integral pairs. There are a few more functions that we need to memorize, what their derivative and what their integral is. So let's take a look at this pair here. I want you to look at the integral we're going to look at. This is an antiderivative that we have not done. Hopefully that's a little surprising because that looks like we could do it. When you see an x on the bottom there, what you might try to do is turn it into a negative exponent. Well, doesn't that just look like a power rule? So what you do is you take this and you add 1 to the exponent. So negative 1 plus 1 is 0. Weird. And you have to divide by that number. So we divide by that exponent. And there we have our problem. We can't use the power rule on this one because that forces us to then divide by 0. So the power rule does not work. And so something else must be going on. Well, what is going on? Let's take a look at a visual representation of that. So here I've got that antiderivative, 1 over, in this case, t. I'm sort of doing the same thing that we did for the second fundamental theorem of calculus. I'm going to use a definite integral to show me what an indefinite integral is doing. So we have the integral from 1 to x, and I'm going to change what that x is, and that value I have plotted right here. So as I change that x value, you'll see, one second here. All right, let's try this again. I think it'll move this time. So this is the value of that definite integral. And so as I move the x's back and forth, you can see it does take a path. And what path is it doing? Well, to help us see that a little bit better, let's trace that path. So you can actually see that it does make a function. But what function is that? Well, that is the function natural log of x, if you can't quite recognize it. If I turn that on, you see it fits all those dots perfectly. And so this antiderivative is going to be equal to the natural log of x. One important thing to note is this only works for positive values of x. And as you can see, natural log of x, this red curve is only on the right side for positive values. So when we write down what we know here, the integral of 1 over x is equal to the natural log of the absolute value of x plus c. And because these always come in pairs, if I know an antiderivative, I also know a derivative. So the derivative of the natural log of x is equal to 1 over x. There. So now that we have a new pair, we should be able to do a few more algebraic problems using them. So that is what we are going to take a look at real quick. We'll do some easy ones and then one slightly harder one. So let's start with a derivative. So this is going to be a chain rule because we have an outside function, natural log, and we have an inside function, 3x squared plus 2x. So take the derivative of the outside. The derivative of natural log is 1 over whatever is in here. So the inside stays the same. So that will be 3x squared plus 2x times the derivative of the inside. The derivative of the inside here, I'm going to put it in parentheses, is 6x plus 2, it looks like. And so if you rewrote that, you'd probably put the 6x plus 2 on top, divided by 3x squared plus 2x. I don't think that factors, but we might as well try. You can pull out a 2 on top, get 3x plus 1. And on the bottom, you can only pull out an x. So you'd get 3x plus 2. So close. We tried. All right, and this one over here, what is the antiderivative of this? Now at first it doesn't look like the antiderivative we know. This is the one that we know. 1 over x is equal to natural log of the absolute value of x. Doesn't quite look like it fits. And so we have to use our one strategy for antiderivatives, the u substitution. And after a little bit of practice, you'll see that the u is going to be 5x squared minus 8. Because when we take the derivative, that gives us 10x. And this x will cancel out that x. So I saw that the derivative of this will cancel that out. So remember, we move the dx over here, and we move the 10x over here. So we're left with dx is equal to du over 10x. So we will now have the antiderivative of 3x over 5x squared minus 8 is going to be u, and dx is replaced with du over 10x. So then the x's cancel out. The 3 over 10 is left over, so I will move that to the outside. And now we have 1 over u, which does look like the new rule we have. So that will be 3 over 10 natural log of u. And we don't care about u, so 5x squared minus 8 plus c is what we've got. So sometimes you won't see this rule happen until after you do a u substitution. Oftentimes that's what happens, not to make it too easy on you. All right, those are pretty straightforward. Let's do one that's a little bit harder. So we got our easy example out of the way. Let's try a harder one. So another big fraction inside our antiderivative. And this one we're not going to use a u substitution. You might try that because, hey, the derivative of x cubed is 3x squared. That might cancel that out. But because it's a polynomial and we have this minus 3x, you're never going to be able to cancel out both of them. So we have to try something else. Well, you have to remember what you learned about fractions way back in elementary school. Is if they have a common denominator, you can add the tops. And so what you can do is rewrite this antiderivative like this. Okay, so hopefully that makes sense now that you see it at the end. These have a common denominator, so you can subtract the top and you'd get back to where you started. We're just doing that step backwards. But now that we broke this up into two smaller fractions, we can simplify each of them. So the first one, 5x squared over x cubed, you can cancel out the x's now. So we cancel out the x's and you're left with an x on the bottom, it looks like. Minus, and this one, I'm going to break this up into two integrals just to make things a little bit clearer. We can cancel out one of the x's, so we're left with 3 over x squared. So I'm going to add a dx here and a dx there. We'll just do them both separately because they're subtraction. Now here you got to be careful. This one uses our new rule. We have something over x. This one does not use our new rule because it's an x squared, and you could have done this one weeks ago. So don't forget what you've already learned. This one will be the integral of 3x to the negative 2, and our power rule works on that one. This one does not use the power rule. That one is simply going to be 5 natural log of the absolute value of x. No u substitution needed. we can just use the rule straight away. All right, let's finish that one up. So we have 5 natural log of the absolute value of x minus, so let's see, the x to the negative 2 becomes x to the negative 1. The 3 is still there, but now we have to divide by that negative 1, so that will become another negative there. And when we simplify all of this together, that will become 5 natural log of the absolute value of x. That does not change. The two negatives become positive. And let's put that in the bottom because there's a negative exponent. So 3 over x plus c. This is a good example because you see one fraction that uses this natural log rule because the x is a power of 1. And then you see a fraction where you don't use this rule because the exponent is 2, and you can use a power rule. So this one uses the natural log rule, this one uses the power rule. It's important to see the difference between them. All right, hopefully that helps with our new derivative and integral pair that go together, and we have a few more to look at in the coming days.